All right, guys. Today we're going to start our conversation about astronomy, how the Earth, Moon, and Sun system operate, and then what are the phenomenon or things that we see here on Earth because of the motions of these objects. Now, for our purposes this year, of course, we're just going to assume that the sun is stationary. It is not in real life. Uh, we will talk a little bit about that later on, but our focus is on the movements of the Earth and what effects those movements have on our day to day experiences and what we see and feel here on Earth. So, first thing we want to talk about is that the Earth rotates around the axis. Now, the axis is an imaginary line. There is no pole that is going through the Earth. So when we refer to things like the North Pole or the South Pole, there is not an actual pole sitting at the North and South Pole. So the axis is just an imaginary line upon which the Earth rotates around. So when we talk about rotating, we're talking about spinning. So if you think about a basketball player spinning a basketball on his finger, that would be rotation. Okay. So the Earth rotates around its axis. The axis is tilted. That's extremely important. So we see this image of the Earth here at the top. That's not really accurate. That's kind of the Earth sitting straight up and down. The picture that you see down here at the bottom is more closely indicative of what the Earth looks like in space. The axis is tilted 23.4 degrees, and that has a big effect on our daily lives, and we'll talk about that effect as we move through it. And the other thing too is revolves. We'll get to the revolution part here in a minute, but the Earth rotates on its axis, spins, and the Earth revolves or orbits the sun. And so the important piece here is that you understand the difference between rotation and revolution. So rotation, again, the Earth rotates on its axis once every 24 hours. So you see the spinning Earth at the top again, which is not completely accurate because that Earth is not tilted. But that is basically what rotation is. It takes the Earth 24 hours to spin one time. Now, to be technical, it takes 23 hours and 56 minutes, but it would be very hard to base our clocks on a 23-hour, 56-minute day. So when the people got together many years ago and talked about how we were going to measure time and how time passes, they decided that they would round the length of time it takes the Earth to spin from 23 hours and 56 minutes and just make it 24 hours. There are ways later on in our calendar that account for that extra 4 minutes there. We'll talk about that a little bit later on. So, your purposes, you need to know that the Earth rotates on its axis once every 24 hours. Now, of course, that rotation creates our day and night. Okay, so even though it may look like the sun comes up in the east and goes down in the west, in reality, it's not the sun moving, it is the rotation of the Earth that is making the sun appear to move. And so a long time ago, people believed that the sun was what was going around the Earth. It's what we call a geocentric model of the universe. They believed that the Earth was the center of everything and everything went around the Earth. And there's not really much to say negative about that because that's what it looks like. Here, as we sit on the Earth today, we don't feel like we're spinning at thousands of kilometers per hour. We don't feel like we're orbiting the sun at thousands of kilometers per hour. We feel like we are stationary. And so when we see things like the moon and the sun and stars move in the sky, it is very easy just to assume that they are the things that are moving and we are stationary, but that is not the case. The Earth is what is doing the moving. Now, the moon does move, The sun does move. We'll talk about that later on. But for this purposes and our understanding of day and night, we need to remember that it is the earth that is spinning, making everything else appear like it's going around us. Okay? So the direction of rotation is counterclockwise, west to east, if you're viewing Earth from above the North Pole. So if you're standing above the North Pole looking down, the Earth would spin counter to the way a second hand on a clock would spin. So what results in the rotation? Of course, the obvious thing is day and night. All right, so we see the sun come up in the east in the morning. We see the sun go down in the west in the evening. Again, that is because of the rotation of the Earth. Only one side of the Earth faces the sun at any given moment. So 50% of the Earth is in daylight and 50% of the Earth is in nighttime all the time. So we'll talk about time zones and the international dateline and stuff a little bit later. But for example, England is 6 hours ahead of us. So right now here in San Antonio, as I make this video, it is 2 p.m. Right now in London, England, it is 8 p.m. So their clocks will switch to midnight 6 hours before ours do. And so there are ways that you could possibly get on a plane on a Tuesday, fly a couple of hours in a certain direction, and be land in another place that is the date is Wednesday. So you could actually lose some time or gain some time depending on what direction you're flying. And we'll talk more about that later on. So Earth's rotation results in our day and our night. And it also results, of course, with our sunrise and sunset. So if we look at this model here, here's a model of the Earth. There's the sun. The sun is 93 million miles away from us, okay, way over here. And so the side of the Earth that is facing the sun is in daylight, and then the side of the Earth that you can't see here would be in nighttime, okay? This line, of course, is the equator, cuts the Earth in half between north and southern hemispheres. And when we get later on and talk about seasons and day and night, you can see here that in this configuration with the Earth on this side of the sun, it is the northern hemisphere. If you look at this like a pie piece, this is a pretty big pie piece that's in daytime. And in the southern hemisphere, the days are much shorter. So in this configuration, the days in the northern hemisphere are longer, and the days in the southern hemisphere are shorter. Now, 6 months later, when the Earth is on the opposite side of the sun, then you can see that it's different. So now the days in the northern hemisphere are shorter than the days in the southern hemisphere. Okay, so we kind of have to understand that that arrangement and the position of the Earth relative to the sun, and that affects, of course, excuse me, our length of day, but it also affects our seasons, and we'll get to that a little bit more later on. Okay? All right, so this is a sunrise and sunset chart for San Antonio, Texas in January of 2021. So, for example, today is the 27th. So this morning the sun rose at 7:25, and the sun will set tonight at 6:08, which gives us a total length of daylight of being 10 hours, 42 minutes, and 31 seconds. Now, if we look at tomorrow, the sun will rise at the same time, but the sun will set 1 minute later. And if we look at Friday, the sun will rise a minute earlier and set at the same time. Saturday, the sun will rise at 7:24, set at 6:10, and then on Sunday, the sun will rise at 7:23 and will set at 6:11. So if you look over here on the length of the day, going all the way back to January 17th, the length of the day on January the 17th was 10 hours, 30 minutes, 41 seconds. The length of the day on the last day of January is 10 hours, 47 minutes, and 57 seconds. So in a span of 14 days, our day has gotten longer by 17 minutes. Now, we don't notice this on a day-to-day basis. Our bodies are not that in tune to notice a minute difference here or there. But you can see here that basically each day in January, we're adding a minute of sun time or daytime, adding another minute, adding another minute, adding another minute. So right about now, during this time of year, we are basically adding a minute of daylight to our day every day. Okay, so what is happening to the time of sunrise between the 17th and the 31st? Basically, it is getting earlier. So the sun is getting earlier, coming up earlier, and the sunset is happening later. And so that causes our days to become longer. Okay, so so that's January of this year. Now, if we fast forward to September of this year, in the fall, okay, notice how the sunrise is at 7:19 and the sunset is at 7:36. So that's a length of day of 12 hours and 16 minutes. But notice how the length of the day is changing now as we move from September 17th to September 30th. So on the 17th, the length of our day was 12 minutes and 16 seconds, or 12 hours and 16 minutes. And then on the 30th, the length of our day is 11 hours and 53 minutes. And so you can see here in the difference column that we are losing close to 2 minutes of daylight during September. Okay, so all right, so here's a video that y'all can watch. This is just, I don't think there's just music to it, and it basically is just a picture from space of what the Earth looks like as it rotates. Okay, so now let's talk about revolution. Revolution is the movement of the Earth around the sun. Okay, so you see in the GIF up there at the top that the Earth revolves around the sun, orbits the sun. And notice that it is not a perfect circle. There are times when the Earth is close to the sun, 147 million kilometers, and there's a time that the Earth is far from the sun at 152 kilometers. It takes 365 and 1/4 day for the Earth to make one trip. Okay, so let's talk about that quarter day for a minute. 1/4 of 24 hours is 6 hours. So another way to say that is that the length of our year is 365 days and 6 hours. Now, if we take that 6 hours and we add them together after 4 years, 365 days, 6 hours, plus 365 days plus 6 hours, do that 4 times, then those 6 hours become 24. And so on our calendar, what we do every 4 years is we add an extra day to our calendar in February to account for that 6 extra hours every year of the Earth's revolution around the sun. So if you've ever wondered why we have a leap day in years that are divisible by 4, we had one this past year in 2020. We won't have another leap day until 2024. Where the calendar in February will go to February 29th. That only happens in years that are equally divisible by 4. The path around the sun is not a circle, as I showed you earlier. The shortest distance between the Earth and sun is about 147 million kilometers and occurs in January. And the furthest distance between the Earth and sun is 152 million kilometers, and that occurs in July. And this may be counterintuitive, meaning or thinking that when the Earth is closest to the sun, then it's hotter on the Earth. And when the Earth is further from the sun, 5 million more kilometers away, that it is colder. But in actuality, our temperatures do not really fluctuate because of that. In other words, our seasons, January, February, or winter, summer, spring, fall, are not caused by how far away the Earth is from the sun. It is caused by something entirely different that we will talk about later on. And that is, of course, right now. Okay, it's the revolution and the tilt of the Earth that causes the seasons. Okay, so the Earth's axis is tilted, and if you'll notice in this diagram that the tilt always is pointed in the same direction. Okay, so in this case, up and to the right. So when the Earth is in this position right here, the northern hemisphere is pointed towards the sun. So the northern hemisphere gets the most intense heat from the sun, and the southern hemisphere gets less. Okay? So again, this would be the beginning of summer for the northern hemisphere and opposite for the southern hemisphere. Okay? Now, 93.6 days later, the Earth is here, and notice that the Earth's axis is not pointed toward or away from the sun. This is fall. Okay, so temperatures are pretty mild. There's not a big difference between day and night. So this would be the beginning of fall for us in the north, which would be the beginning of spring for those in the south. 89.8 days later, we're in this position where the northern hemisphere is now pointed away from the sun. So now it is winter in the north and summer in the south. So to give you an idea, the Winter Olympics, the Summer Olympics many years ago was held in Sydney, Australia, which is in the southern hemisphere. And even though it was the Summer Olympics, we could watch it here in America. We were watching the Summer Olympics at Christmas time. So yes, it is a little weird to think that Santa Claus, when he drops off his presents in Australia, should be wearing shorts, a tank top, and chanclas, whereas in the northern hemisphere, he needs to dress warm. And then 89 days later, in March, we reach the beginning of March, called the March equinox or the spring equinox. So that's the beginning of spring for us. Okay, so spring to summer to fall to winter, and that is what causes our season. So it's basically the revolution of the Earth around the sun combined with the tilt of the Earth's axis. If the Earth's axis was not tilted, we would have the same season on Earth wherever we live all year. Okay? So we'll talk more about equinoxes and solstices as we move a little bit forward. Okay, the average distance from the Earth to the sun is called an astronomical unit, or AU. So for us, our purposes, the average distance is 150 million kilometers, or 93 million miles. So we use that as a measurement, and we call that 1 AU, 1 astronomical unit. So if we say something is 2 AUs or 3 AUs or 4 AUs away, then basically what we're saying is it is 2 times the distance that the Earth is from the sun, 3 times or 4 times the distance that the Earth is from the sun. And that is what an astronomical unit is. Okay? So hopefully this explains it. Again, if you have any questions, please join us in Zoom every day, and I'll be happy to explain some of these phenomena in a little bit more detail. All right, guys. See ya.